Today we're going to learn something that can be useful in real life. We have a pile of candies and we want to divide this pile of candies in groups of 5, first in groups of 5, then 4 candies are left. If it's a group of 5, 4 candies are left. If we divide this pile of candy in groups of 7, 6 are left. Now we're sure there are fewer than 50 candies in this pile of candies. What is the exact number? Now first, let's think about algebraically how we translate this problem into mathematical representation. Let's assume this exact number of candies in this pile is n. Assume this exact number is n. Then we know that when n divided by 5, we'll have some numbers, the quotient, which we don't know, but then the remainder will be 4. And then the same number, when divided by 7, again, there will be a quotient that unknown, which is different from this quotient, and the remainder is 6. The question is, what is this n? And we also know that this n is less than 50. So how we solve this question? You see, if we know the quotient, let's say the quotient is 1, then we know from one equation that this n will be 9 from first equation. But that certainly does not satisfy the second equation. So here really, there will be such n. When you divide by 5, it has some quotient, but remainder 4. And this n divided by 7, another quotient, different quotient, remainder 6. So one way of doing this kind of question is, all right, let's start with one condition and make sure this n satisfies one condition, and then slowly, with all those numbers satisfy the first one, try to see whether we find a number that satisfies the second as well. So this is a kind of brute force searching. So solution number 1. Let's look at the numbers n such that when you divide by 5, the remainder is 4. And we know such numbers are pretty easy, right? If the quotient is 1, we know it's a 9. And the next number, adding 5, we know 14 is also such a number. Okay, what's the next number? 19, and 24, and 29, and 34, and 39, so on. So here I'm construct or listed such numbers such that the number divided by 5 has a remainder 4. And now I'm going to just searching this number to check each number whether that satisfies the second condition. When I divide by 7, has a remainder 6. 9, no. 14 divided by 7, remainder 0, no. 19 divided by 7, remainder 5, no. 24 divided by 7, remainder 3, no. 29 divided by 7, remainder 1, no. 34 divided by 7, quotient 4, remainder 6, yeah. We found 34 is the first number such that it satisfies the first condition, which is what we start with, and then the second condition by just manually checking. So 34 is the answer. Of course, we can do this searching by first construct a sequence satisfying the second condition, and then we check the number one by one whether that satisfies the first condition. All right, let's try to do that way. So for numbers that n divided by 7 has a remainder 6, okay, the first number will be a 6. The second number is plus 7, 13. The next number will be 20. The third number, the next number will be 27 and 34 and 41. Let's see. So 6 divided by 5, remainder 1. So it's no. 13 divided by 5, remainder 3. No. 20 divided by 5, remainder 0. No. 27 divided by 5, remainder 2. No. 34 divided by 5, remainder 4. And you're good. Of course, we find the same number. Right? So here, the first solution is we are using a very, very basic approach. And it's kind of a brute force way of doing things. By constructing a sequence satisfy one condition, and in the sequence we're going to check one by one manually to see if the number also satisfies the second condition, and once we find such a number, we're done. So in a different way, I'm saying that I'm looking at two sequences. There's the first sequence is n divided by 5 has remainder 4. So these numbers are 4, 9, 14, 19, 24, 29, 34. And the second sequence is n divided by 7, remainder 6 sequence, which the numbers are 6, 13, 20, 27, 34, 41, and so on. Now, we really want to find the common numbers between these sequences, which are going to satisfy both 1 and 2, right? And you see the first number is 34. Next question. If the first number is 34, what is the next number also satisfy these both conditions, n divided by 5, remainder 4, and n divided by 7, remainder 6? It turns out, if you have a 34, then 34 plus the LCM, the least common multiple of 5 and 7, and times any multiple of that, let's say times a k, also going to satisfy these two equations. Let's call it equation 1 and equation 2. Why is that? Because if for the 34 is already satisfy 1 and 2, but the LCM of 5 and 7 and multiply by any k, this number when divided by 5, it has remainder 0. Divided by 7 is also has remainder 0. So this is not going to add any remainder to the remainder generated by 34. So it's also going to satisfy both equation 1 and 2. And these are all the numbers that are going to satisfy 1 and 2. All right, now we look at another solution of solving this problem. And this solution is pretty neat, because solution 1 is kind of a brute force way, which will say that if the numbers are pretty big, it's probably going to be a difficult way of doing it. And solution 2 is a neat trick and only going to work for special cases. In here we observe that when n divided by 5, the remainder is 4. N divided by 7, the remainder is 6. Realize the 5 and the 4 difference is 1. The 7 and the 6 difference is also 1. So when the remainder 4 for n divided by 5, if I plus 1, n plus 1, then the remainder divided by 5 is 0, correct? So n plus 1 is a multiple of 5. And here 7 is 6, n plus 1. If n divided by 7 remainder 6, then n plus 1 divided by 7, the remainder is going to be 0 as well, or 7 or 0 as well. So n plus 1 is also a multiple of 7. So which means n plus 1, 5 divides n plus 1, and 7 is also divided by n plus 1. So n plus 1 is going to be the least common multiple of 5 and 7 and a multiple of that. So first number is n plus 1. Different way of saying it, n plus 1 is a multiple of the LCM of 5 and 7. LCM of 5 and 7 is 35. So n plus 1 could be equal 35, could be equal 70, could be equal 105, and could be equal 140, and so on. But we know that n plus 1 is going to be a number less than or equal to 50. So n plus 1 is actually indeed 35. So n equals 34. Again, I want to say that solution 2 only works if the divisor and the remainder has a difference that is a constant. In this case, the difference is 1. But if the difference is 3 or difference is 2, it's also going to work. But if these two differences are not equal, then this technique does not work. Now, for this kind of question, a general approach of solving this is using a technique called Chinese remainder theorem. And that description is going to be beyond this lecture. If you are interested, you should look at videos on MathCup titled with Chinese remainder theorems. There are 2 videos on that topic. So you should check it out if you are interested of learning more.